this was X. All right, now go back to option. Okay. Okay. Excellent. All right, so we have, there's John. Boom, excellent. Let me quickly see if I can generate any audio. Switch on a second. Four. I just a little bit on that. 111. And I think I'm good.
Hi, Adrian. Can everyone hear me?
Yes, we can hear you. That's excellent.
Perfect.
We're recording, so we're ready to go.
Awesome. Sounds good. Do we have everyone, or should we wait another minute?
Maybe wait a few more minutes, not a lot of minutes. So just 2 or 3 minutes.
Sounds good. I'll also go ahead and share so the notebook I'm using today, students can feel free to take a look at later. It's got some links to various things, so that's in the Zoom chat, and I'll make sure that you've got that in email too, Adrian.
Oh, I see. So if I click on the Zoom chat, this is what I get. That's excellent. And you want to start sharing now? I can stop sharing. Oh, there you go.
How's that look in terms of screen size? Can people read this okay? Shall we maybe have this size?
Yeah, let me check with we can hear and see very well, but let me check with, let's say, with Ahmad. Ahmad, can you say a few words, and also can you tell me if you can see the screen properly?
Yeah, everything's perfect.
Okay. All right, so in terms of audience, we have 10 high school teachers, and then we also have 9 undergraduates and 3 graduate students. But the way we run the class is in hybrid mode, which means that some people are in the room, some people are elsewhere, but watching through the Zoom, and then a lot of people are unable to join at this time, but they watch the recording, and I have weekly meetings with them in which we discuss, so what was the theme this week? What did you understand? Specifically with the high school student teachers, my main question for them every week is, so they are sponsored by the Center for Quantum Technologies. And our goal is to make sure that what we present here is useful and applicable, immediately applied to, or could be used as is in some sense in the classroom. So there's one teacher that teaches in middle school, and then there are 9 that teach physics, math in high school at the various levels. So my question to them is, given the theme for this week, and then you will become part of that theme with today's lecture, John, do you think that what we presented is accessible? Would you be able to use it in your classroom? And if not, what is it that we can do to simplify it? And in what way? So that's just the basic idea behind what's happening. So is Ahmad also another part? Connecting, and other people might connect, but I'm not going to say anything when they connect. I'm just going to let them in. So
Sounds
that's
great.
yeah, good. That's the basic background. So essentially, we could, in fact, start now.
Okay, perfect. So as I said in the beginning, there's a link if you want to take a look at this notebook that you can use, download at any time. You can also, through a browser, look at it in Wolfram Cloud. So again, if there's anything that you want to send questions about later, do feel free to send email to quantum@wolfram.com. Also, feel free to reach out to me directly, John McNally. I'm also going to be very much involved in the Wolfram summer programs that are starting just next week. Technically, they're already sort of started with some of our physics tracks, but the instructors that we have in courses like this, before joining Wolfram Research, I also taught high school, and so there's a track at our summer programs that we call educational innovation. And 2 years ago, I joined this educational innovation track at the summer program because I was using Mathematica, which is the software that you're seeing here that runs what's called the Wolfram language. And you can use this in your classroom because it's designed to be much more similar to like a spoken language as compared to a programming language, right? That's in the sense that you want to try to express what you're doing in terms that a computer can do something with it, but it's a little bit more the way that you might think about tackling a problem. And so hopefully you'll see some examples of the way that design looks like. But anyway, before joining the company, I was using this in my classroom, and so I joined the summer program because I wanted to see what was new and some additional tips and tricks and sorts of things that could be used for bringing skills in terms of making the students able to work with code, right? So we have a variety of tools that we try to make working with computers more accessible than typically what you might think of when writing code. But also, especially in the sciences, students really found this idea of, even if it's not a branch of science that I as a student personally care about, I'm still sold on this idea that, knowing how to write some code in a language that I can accomplish things with without having to write too much code, this is something that really appealed to my students when I was teaching. So at any rate, for this reason, I joined the summer program 2 years ago, and one thing led to another, and I decided to join the company. So that's a brief background. So if anyone, I'd be more than happy to stay in touch either about coming and collaborating with us at the summer programs in future years, or just if you have questions about how any of this can be useful in your classrooms. So without further ado, let's sort of get into some tools that we have for quantum computation. So, one thing that we do specifically for quantum is there's a framework that we've developed that tries to allow you to frame quantum problems more similarly to what a physicist might think of a quantum problem as compared to, let's say, someone who's working with software engineering all the time, right? So this is just some preliminary things of how one would install that if you're wanting to work with this in your own version of Mathematica. But what you would do is, if you want to create a quantum state, we have just a function that you would create a quantum state. And so let's say I want to make a random state. Now, one of the things I like about teaching quantum is that it allows you to make connections with many other topics in mathematics that students might say, well, why are these sorts of things useful? What are they applied for? So let's say that I want to take a look at what this state would be represented as a vector. So if you're teaching about complex numbers or you're teaching about vectors in your classes, quantum, even though we can introduce many concepts in quantum without having to get into any of this formalism, if you do want to make those connections with people who are teaching mathematics in your departments, I think there's a real opportunity here for connecting what does a vector do? Why should I as a student care about vectors with something that we really do use them for, which is modeling quantum states. Same thing with working with matrices, right? So this random state that I've generated can be modeled as a matrix. And so again, I think having a point of connection between mathematical formalism and quantum concepts that you can sort of tie together with code, right? So for example, if I want to see what the state looks like as a matrix, this is more or less what one would expect to do. I ask for it as a matrix. Now, this also lets you draw a connection with geometry ideas that you might be learning about in courses. So here we have a different random state than the last time I ran this code. But one way of representing quantum states that is a very common way of seeing what a qubit is doing is with this thing that we call a block plot. So, here you might have a state that's either black or white in some of the formalisms that you're looking at, but you might also decide to measure that state not necessarily along the black or white direction, so to speak, in the space of things that this state could occupy, right? So this plot is another way, and I think this is one of the things that's really key in developing quantum, and is important to have instructors sort of bring these concepts to their classrooms and works directly with students, is to get actual data and do the educational psychology research on, out of the many representations of these ideas that are out there, which are the ones that students sort of find most natural, and how can we also tie that in with other areas of the curriculum, right? So how do you make a block plot? Well, basically there's a mapping that you can ask for just with a little bit of code in either the regular Cartesian coordinate system, or in some courses of math study, the more advanced high school students in the last school I was at, they would get into, okay, well, what's the deal with these spherical coordinates? We don't just have to work in the Cartesian coordinate system, excuse me, but there's all sorts of other coordinate systems that are possible. And so, again, having quantum as this, scientific framework for thinking about all sorts of problems throughout the world gives us also ways to connect to mathematical representations that are things that are very likely to be in our courses that our students are engaging with anyway. So again, you could have an entire geometry sequence in math courses while also talking about how do we work with block plots in the context of quantum. And so you can check your work and what's going on by sort of generating these states and then saying, okay, well, let's have some code quickly generate so that I can check. But we could also talk about, if you wanted to build these up step by step, how would we actually do it in terms of starting with the coordinates that would represent where the state is in the space of possible things that it could be, and then how do we turn that into a picture like this? And so, again, the theme I'm trying to make here is that there's ways of tying together all sorts of different concepts that we would want to be teaching anyway on one context. And so here, this code is a little bit more involved because it makes it manipulative, but let's say that someone has created this manipulative already. You could then see, if I apply different operators to these states in terms of a circuit, well, what's going to happen to my quantum state as I apply different rotation angles to that state. And so again, we can use manipulatives as another way of exploring what's going on. And I'll show some more examples. Let me zoom this out just a little bit. Let me know if any of this is too small, but it should fit a little bit around the screen this way. So, another concept that one can study, not just in the context of quantum, but in a lot. So again, the code is a little bit more involved because it involves making some random choices of different rotation angles that we could apply. So after we've sort of seen what these rotation angles do in terms of moving a state around on this block sphere representation, you could create a quick little animation that shows what happens if we apply a sequence of random quantum operations to our state and see how the state might evolve. And so here, I've picked a particular way of defining what it means to apply random operators, but a student might be curious, well, what if I only apply random operations in 2 out of these 3 possible directions rather than all 3 of them? What would that look like? And so you can immediately let's say that we'll do this actually. Let's remove this as a possibility. Let's generate these states. This will take a minute to run. And maybe at the end, we'll come back and generate this animation. So again, when you're generating more things, sometimes it takes a minute. So again, this is a way of working with manipulatives and animations as well. In fact, let me pause this one just for a minute. That one takes a little bit longer than I recalled to actually evaluate. Okay, but another thing I want to jump into are the practice problems. So one of the things that I really always found that I liked to do when I was teaching is just jump into the sort of learning goals and the problems right away. So let's also explore not just quantum, but how can some of these other concepts like probability, which again is one of these mathematical concepts that's very tied in with the study of quantum theory, how can we explore this in a way that also brings in computation? So if we look at some of these practice problems that you have from this week, so there's all sorts of full courses that we can take a look at. And so I'll briefly stop sharing this screen and hop over to showing my browser here, where there's courses like this Introduction to Finite Mathematics, which is one that I authored, and then also a very excellent course on Introduction to Probability. And you'll see that in these courses that I like to use as sort of a flipped classroom. I was very happy to be able to offer one of these myself. But even before that, when I first saw these, I said, this would be a really great resource to, let's say that you wanted to have a course where the students need a little bit of background on probability, right? So you can remind them of how some of these things work, how probability can be defined, as well as exercises and some space that they can take a look at writing their own code. So let's say that I want to take some code that we've seen in the lesson and explore it a little bit further if I'm a student. So let's find where we have some code. So here, this code is saying, well, what's the probability that the result I get is divisible by 2 if the random variable is distributed according to what a 6-sided die might be? So we could evaluate that and get a result. Let's say that I want to now say, well, what's the probability if I'm a student? How about I want to check what's the probability that the result is divisible by 3? Or what's the result if the if the result is divisible by 5, what's the probability of obtaining that, right? So the student can take examples that they're seeing in the video and text lesson and then explore it with code, all from the same place in their browser. And the other thing I really like about these Wolfram U courses is that they're actually completely free. So anyone can sign up for a Wolfram account, and then through Wolfram Cloud, they'll be able to access these Wolfram U courses. So, I always like to show people these resources because a lot of people don't realize there's so many free courses out there. And so not only in the context of finite mathematics and probability, but also there's courses on calculus and elementary algebra and all sorts of things that high school students would find useful in this sort of flipped classroom setting. And many of the courses also have these quizzes, which the students can check their understanding. Are they getting the concepts so that then they can move on to the next lessons. So again, I hope that many of you will find courses like this useful. At some point in the future, we would actually love to do one on quantum specifically. We've had some thoughts and some talks about how to do that, but we don't have a date yet set for when we're going to try to create one specifically on quantum in this full course setup. There are study groups which are also free that are offered through Wolfram U that are on the topic of quantum, but it would be really nice to do like the full video text quiz treatment that many of our other mathematics courses have on Wolfram U here. Okay, so let's get back into your practice problems so I can show you how you can explore some of these computationally. Now, the first one talks about this classic game where you roll 2 die, and so we can define some probability distribution where the result is rolling 2 6-sided die. Now, the probability function that we get by doing this is one of the things that I always find really interesting when teaching students about probability, right? Is that if you treat each die separately, naturally, let's say that one is red and one is blue, then the probability of any particular combination of what you get on the red die and the blue die is the same. However, if what you care about is the sum of those dice, so in other words, again, we ask for the probability of adding these 2 die coming up to a particular number, where the 2 die are distributed according to this probability distribution that we've set out, which is just rolling 2 of these 6-sided die. Then you see that, again, you can spell it out in terms of the specific numbers, but sometimes a picture is worth 1,000 words. And hopefully, you can see that the code required to do these things is not so much, right? many of the function names are what one would expect. I think the most exotic here would be a product distribution and a discrete uniform distribution, which are sensible names, but perhaps maybe long names. But if I want to make a probability distribution function, if I want to plot it, the names for these sorts of things, if I want to compute probability, they're what one would expect if you're just stating what you want to do. And so the language is designed in such a way that the computer can take these names of functions and evaluate things where people, yes, this is code, but it's code that's designed to be more like what a person would hopefully think in terms of. So at any rate, let's take these two visualizations here real quick. And this can be a really difficult concept for some students to grasp, right? But sometimes just seeing the difference in terms of, if I had a red die and a blue die, yes, getting a particular combination on the red die and the blue die is a space that looks like this, and everything is equally likely. But if what I care about is summing those dice, then this is what the space looks like, and I get a much different probability distribution, where of course, rolling a 7 on two 6-sided die is the most likely outcome. And so you can build these up in terms of more elementary functions, but we have these higher level functions where, if what I care about is just double checking, let's say I was by hand was the learning goal to calculate this. Can I just check, did I do it right? Yes, you can get the result fairly quickly. Then there's a second part to this question, which I found interesting. And this is one of the things which, as a computational exploration, is sort of the reason why the company was founded in the first place, is to sort of facilitate people that want to do these computational experiments and explore problems more fully. But it then asks, okay, so this is the game, which we've sort of understood the probability distribution of the game. But then if now we bring in the concept of betting a chip, and maybe I can lose a chip or win 4 chips, and then is that fair? That's a really interesting question. So one way of tackling this is to compute, let's say, the expected value of what would happen. So in terms of code, if the sum of my 2 die, which again, they're distributed according to this game distribution that we've defined. So if their sum is 7, I'll make this maybe a little bit bigger so that you can see more easily again, then I get the 4 chips, plus I get to keep the one I started with. But if the sum is not 7, then I'll default to losing the chip that I wagered. And so the expected value of playing that game once is to lose 1/6 of a chip, so to speak, right? So in other words, that's on average the payout if I play this game repeatedly. And so we could also explore what happens. Well, what if the payout isn't 4, but it's just some variable? I could set the variable name and see that this formula tells me what the expected value of playing this game is repeatedly. So the game as framed, we could say, well, the expected value is that I lose chips if I keep playing this game. And so maybe I would say that's not fair in that sense. But a way of maybe defining a similar game that we could think of as being more fair might be to say that, well, if I made this net payout equal to 5, then the expected value of playing the game repeatedly would be 0. In other words, if I just kept playing for a while, I would expect to break even because of the way that the dice probabilities are related to this if statement about what we're getting paid each way, whether or not we win or we lose. And now this brings us to another interesting point. So that's one way of thinking about, okay, well, how would I think about this game in terms of expected value and fairness? But we might also want to bring another twist into this. And so Markov processes are something during this course on finite mathematics. Now, let's say that we are also wanting to model that maybe the player in the house that are running this game don't have unlimited amounts of chips that they can actually use to play this game. So let's imagine that there's only 10 chips and the player doesn't want to lose their last chip. So in other words, if we start with only 1 chip, we're just going to, with probability 1, we're going to stop playing and we're just going to keep our 1 chip. But let's say that we start with 2 chips. Well, if we start with 2 chips, there's a 1 in 6 probability, again, computed previously, where I can win this and get 4 chips. So then I'm up to 6. But then once I'm up to 6, I've got a 1 in 6 chance that, oh, now I'll get to 10. And if I get to 10 chips and there's only 10 chips total between the house and the player, then the house can't actually play this game anymore, right? So the player can't play because the house has nothing left to give if they win. So with probability 1, the player might sort of bust the house, so to speak. But more likely, with 5 and 6 chance, the player would actually lose. And so, if there's only 10 chips in this game, we might model this game as a process that looks more like this. And if you want to see what the code looks like to do that, the most complicated thing is defining what this game looks like. So don't worry about that part. One thing that we can also do, let's say that we run into something where there's maybe a little bit more scary code at some point, but we're still wanting our students to engage with it. What we can do is we can hide that part. And then, once we've hidden that part, we're focusing on, okay, so we're defining a discrete Markov process, and then we're making a graph of that process. And how is this process defined? Well, this is a little bit of a complicated game. And so the matrix that defines this game is maybe a little bit more complicated to write out with code. But if we want to hide that detail, we can always hide that detail, right? And then we can even hide the input totally if we just want to focus on the output here. So, all right, so let's say that it wasn't just with 10 chips, but let's say that there were 100 chips sort of in the pool between the player and the house. And again, if you want to see what code actually makes this graph, it's here. But, you could say, well, another way of thinking, so what's the probability if I just keep playing this game that I wind up losing all my chips? Or, if I start with enough chips that, the house can't even start playing because they can't possibly pay me 4 chips, then, we actually can't play the game. So the player won't bust, so to speak, if they have already all the chips. But we can see that, the expected value of this game is such that with almost any amount of starting chips, so even if the player and the house are equally wealthy in chips, so to speak, the probabilities are such that if you just keep playing that game, the player will run out of chips before the house does. So in that sense, maybe that's not fair. But if the player starts with, I think it was 90 chips, it turned out. Yeah, so if the player started with 90 out of the 100 available chips in this setup, then it's a roughly 50-50 chance that either the player will bust or the house will bust if this game just keeps getting played until someone runs out of chips. So, I think being able to, explore problems like this in many, many, many different contexts, right? So, I mean, you could easily imagine a problem such as this that is sort of framed as, compute the expected value of the game. And so, sure, you can do that. But then you might also start to have your students elaborate on that question of, okay, so the expected value of this game in the context that it's presented isn't quite fair to the player, but could it be fair? And so we could either adjust the payouts so that, or so we could also say the bet amount. So again, we could make these both variables, and then we see that as long as the ratio of the payout to the bet is 5, then that's another way of thinking of this as a fair game in terms of expected payout. But then there's also this other detail that we could get into where one side or the other might run out of chips. And so based off of the way that the probabilities are structured, you see that, this is not quite what one might call a fair curve in this sense either. And then there's places along it where, okay, maybe we could argue that this is in some sense fair. But, there's a lot of space to explore lots of mathematical ideas just in the context of this one question that's sort of very seemingly concrete, but then we can spin off all kinds of related ideas. So, and then let me also just talking about probability. So this other problem, which again, let me bring that down here so that we can remind ourselves what it was. So, if you're wanting to roll 3 dice and say, what's the probability that the sum of these 3 dice is not prime? How can we verify our answer? Well, okay, so we could define now, let's say that we're rolling 3 6-sided dice rather than just the 2 that we had before. And we can compute what's the probability that the sum of the dice is not, that's what this symbol means, in the primes. And we can say that the 3 dice are distributed according to this distribution, and we can compute an answer. And then the important question, right? So this is in one sense verifying because, okay, there's some code that can be run in order to return a result. And so if the code runs and gives a result, that's in a sense a verification. But then we might also say, well, let's say that I wanted to understand the algorithm involved in doing it. so that we could, let's say, check that the code was running properly and there wasn't some bug somewhere. Well, we could then go into more detail and look at the probabilities of getting each result and then figure out, you know, which ones are prime and sum those up, right? So again, the language is designed in such a way that you know, you can quickly frame problems like this and have the computer take care of the details, right? But then you can also dig in by using different functions in order to understand, okay, well, what might some of those algorithms be that are arriving at a end result? And so it's really, and this is the reason why I used it in my classroom, was, you know, you can just use high level functionality to very quickly compute something that might be relevant to a question that comes up in science, right? Or a question that comes up in this particular game context, right? Just out of curiosity. And then the students might say, well, how does this probability change? In fact, let's do this maybe. So let me, on the fly here, let's make a plot where instead of having just our 3 dice, let's see, how does this change if now I'm going to make this a variable? So now, well, actually, we'll come back to that. Yeah, let me not spend time on that. But what I was going to say is that we could make this a variable so that we're rolling more than 3 dice, and we could explore how does this probability evolve as we're rolling more and more dice. So maybe if we have time at the end. But again, I want to make sure that we have time for sticking with quantum.
John,
Yeah, do you have a question as well before we move on back to the quantum?
yeah, I do have a question. It's a simple question, but then also to remind anybody who has joined in, if they have a question, they could in principle stop you and say, hey, I have a question.
Please, yes, absolutely.
My question is, I know how to type in the not belongs to, but what's the symbol between the D1, DT, the D2, D3, and the 3 dice? What's that symbol and how do you get it?
Yeah, so this is called the distributed symbol. So there's a lot of shorthand notation that we use sometimes to make things more you know, readable, right? So if I hover over this, it says distributed, which might be a little bit small to see on your screen. But then if I ever have a question about what something is doing, I can say, okay, distributed. What do you do? Question mark distributed. And then I can even follow a link that will open a notebook here. Can you see this notebook now that says distributed here at the top?
Yeah, so I could type in Wolfram Alpha, I could type distributed instead of that symbol, right?
Yes, yes. And so we can see that instead of this symbol, and then how do I get that? If I, as a keyboard shortcut, type escape, dist, escape, I get that special symbol. But, you know, if I didn't remember that and I didn't feel like looking it up, I could take this same bit of code here. So let me take this and let me, instead of using the fancy symbol that I think is a little bit more readable, but let's instead do it like this. And let's just say distributed. And we'll do it like this. This should evaluate to the same thing, right? So again, and same thing with this symbol here, right? So if you don't know how to type in that symbol, I could also say that I'm going to use the function not an element. And the thing that is asserted to not be an element is this sum. And what is it not an element of? It's not an element of the primes, right? So these are the exact same things in terms of what the computer actually does, but we offer a variety of ways to input things, right? So like if you're seeing these symbols in a mathematics course, then you know, you can make contact and the students don't have to have that cognitive load of thinking, okay, well, what are these brackets? Like this is complicated. You know, this reads more like what you would see in one of your math courses. Whereas, you know, this does the same thing. And in some cases might even be easier to type once you're familiar with you know, typing it, but it's, you know, an extra bit of cognitive load that you don't want to introduce to your students right away, I would say, right? So again, anytime that there's a symbol, there's always like, and so if I escape, dist, escape, we can type in these special symbols. You can also copy paste it, right? So if you ever see a special symbol and you just want to put it somewhere, you can grab it and put it anywhere that you want to use it. So yeah, so that's a very good question, is how do you get some of these special symbols? Okay, so before getting into quantum, any other questions just about you know, the relationship between computation and you know, mathematical thinking and anything like that? I'm happy to pause for quick questions if we have any before getting back into the quantum thread. Okay, sounds like we'll move on. So another one of the things, how do we create, this particular quantum circuit in Qiskit, right? So there's a lot of tools out there, right, for working with quantum. So, of course, there are certain things that you're going to want to use Qiskit, even if you're coming from using Mathematica. There might be particular functionality, especially if you're wanting to connect to real quantum hardware that's out there. A lot of times, many of the interfaces will be through a Python library that maybe someone has out there, right? And so if learning to code in Python is part of the learning goals for your course, then we also support that from within this environment too, right? So if you want to type in Python code into this environment, you certainly can. And so that's an option. But another thing that we try to have for convenience is, especially in the context of quantum, let's say I want this quantum circuit. So what are the gates? It's X, H, X, H, X. So let's just define our quantum circuit. So, okay, here's a quantum circuit operator. So then let's turn this into a Qiskit circuit. And the first time that this evaluates, it will take much longer because it's installing the necessary Python behind the scenes to work with Qiskit, since that's a Python library. But since I already did that ahead of time, okay, so now we have a circuit in Qiskit. I can even run this Qiskit circuit and get back a quantum state. And this is the result that's predicted. I can then do exactly what we were doing before of look at a block plot, let's say, and I can check. So is the quantum circuit operator that I defined just purely in terms of our quantum framework equivalent to the Qiskit version? And if you evaluate this, the answer is yes, because when you run them, you get the same quantum state. So we can also then explore then though what's happening to the state after each part of this operation that we're doing. So we start with what we might call the register state, where this is going to be in the 0 instead of a 1. And if we apply the X operator, then our state flips on this block sphere down to here. If we apply an X and then an H, we get a state which is now over here on the block sphere. So you see that it isn't a 0 or a 1, but it is this other definite state, which is on the space of possible things that the quantum state could occupy, but it isn't a 0 or a 1, which is kind of interesting. So then we could keep going. You see that it stayed in the same place, although one thing that this isn't showing are some details related to what one would call the phase, but that's a detail that we don't have to get into. And so you can sort of walk through what's happening to what's happening to the qubit as you're applying each of these operations. So at each point, it's in a definite quantum state. It's just not necessarily the 0 or 1 quantum state. But that's if we're not measuring. So let's say that we also want to say what happens to the measurement probabilities if we measure, is it 0 or 1, right? So, here, if we start out with just our register state where it's definitely a 0, and then we measure it. So here we're coupling our qubit to us, which are some big classical system, and we're measuring what's this qubit. We get probability 1 that we get the 0 because sure enough, it was in that state. And if we now apply this X operator so that we're down here, okay, we now are sure to get 1. If we have applied an X and an H so that we're not in the 0 or 1 state, we're definitely in this state over here on the block sphere. However, if we then insist on measuring, is it a 0 or a 1, now we get a 50-50 chance of the measurement result being a 50-50 result. And notice that this is not the same circuit as this, because here we've added a measurement operation, right? So you're taking something which was definitely in this state that wasn't a 0 or a 1, and you're insisting on measuring it, and then we'll no longer have a 0 or a 1. So the block sphere representation isn't going to be this anymore. But these are the measurement probabilities that we would get. So hopefully, by going through pictures like this, so again, when we're back to here, it's definitely back to the 1 state, and then it's definitely back to the 0 state. So, by being able to go through manipulatives like this, I think it really helps for being able to go over some of the subtleties that have to do with people tend to think, especially students, that quantum mechanics is somehow strange. And okay, sure, it has some things that might be a little bit counterintuitive at times, but if you can go through comparison here and say, if you just apply these two operations, an x and a h, to your thing that started out in the zero state, it's still in a definite quantum state. It just doesn't happen to be the zero state or the one state. It's some other quantum state that we can still represent visually as what that state is. So that removes, I think, some of the mystery. But then if we insist on measuring, okay, is it a 0 or a 1? Well, it wasn't either. But if we insist on trying to measure that, then we're gonna get some probability distribution of either getting a 0 or a 1, because we took something that just wasn't a 0 or a 1, and we said, well, I'm gonna make it conform to that measurement set of possibilities. And
but it would be good to point out that if we were to measure in a different basis, we would get a minus.
Correct, yes. Because if you, so let's say that we instead of so here, if we change this to say, well, instead of measuring in the 0, 1 basis, let's say that I wanted to just measure in the plus minus basis, then we would get the result that you would expect, which is that, yes, it is definitely still this minus state. We only get this probability because we're insisting on measuring in the plus minus basis in this example. And so, again, the code for making a pretty graphic, might look a little bit intense, but most of these are just options for what size to make the graphics. The meat of the code is actually a lot simpler. But so if we change what this measurement operation is, so let's maybe do this. So let's make this a quantum measurement. Whoops, can't spell today.
And then we have a question from Elmar.
So let's say that we want to measure the plus. Assuming I didn't make a syntax mistake here, that should run. Oh, nope. I've mistyped something here. But yeah, so while I'm figuring out what I mistyped, what was the question?
And just that I don't know if I hear it right. Is it basis or phases? Phase or base?
Basis.
Like B. Okay.
Let's see. Did we get the? There we go.
So I don't know exactly, but an analogy for basis would be from Bologna would be currency, maybe. Like I want my result in euros. I want my result in Indian dollars. I want my result. The phases would be from Paris, Texas. It's basically a different thing, and it doesn't affect the measurement. Like our answer is -0, but you can't see it if you measure it. It's still 0 or 1, but it's going to be 0. Yeah. So here we're just talking about basis, would be from Bloomington, and it's about kind of currencies. Well, how do you want your change? I want this currency, Italian lira, for example. Okay, well then, all right.
Doesn't make sense anymore.
Yeah, I like to think of basis sort of in terms of if something is northeast of you, and you say, well, is it east or west of me? Okay, you can kind of answer that question, but that's not the whole story, right? And so this question of basis and quantum states is very similar, right? So I figured out what typing mistake I made. So now I'm measuring not in the 0 or 1, but I'm measuring in this other basis, we would call it, for representing the quantum states. So now let's look at that same circuit, but now my measurement operator is not in the usual 0 or 1. I'm now measuring along this plus minus axis, right? So now if I start out with something that was definitely in the 0 state, but I'm not measuring 0 or 1 anymore, I'm measuring, is it plus minus? Now I have a 50-50 chance of getting the plus or the minus. It was definitely 0, but I didn't want to measure that. I wanted to measure, was it plus minus? And so now I get this probability distribution right away, even though I know I definitely started with a 0, and then I measured in something that is not asking the question, is it 0 or 1? It's asking the question, where is it along this axis? And you can see, well, it's pretty much right in the middle. So that makes some intuitive sense.
I'm very new, but to this quantum computing, can you measure two things at the same time?
You mean two bases?
Two bases.
No, actually, I have a video to share with them from Bazirani, where he says if we want to talk about the uncertainty principle, usually is described in, you know, if you know where something is, you don't know how fast it moves, or the other way around. But what he does in that video, which is a very short video from Berkeley, he says we can get the same basic idea from trying to trying to find the actual information as measurement in two bases at the same time. If you get good accuracy in one basis, you lose the accuracy in the other one. That's the thing that you were asking.
Yeah,
So,
that's a very subtle question that I'm Adrian. I'm sure can provide lots of resources for answering that sort of in more detail because it's very deeply tied in with the mathematical formalism in terms of what the math answer to that is. But conceptually, there's a lot of really interesting ways to think of it.
Yeah, so we get this uncertainty if we switch to the basis plus minus in the beginning, and then we lose it when we measure that minus.
Yeah, so now if we've applied the x and the h, so now again, we're definitely in the minus state. So if I had insisted on saying, all right, I would like to measure in the 0 or 1 basis, recall that was a 0 or 1. But if I let myself just measure a different question, so I'm no longer asking the question at this point, is it 0 or 1? I'm just asking, is it plus or minus? Well, it's definitely minus now, right? So the uncertainty is not really dependent on what the quantum state was after applying these operations. In both cases, it was definitely the same quantum state. And the thing that changes where the uncertainty comes in is I'm interacting in order to actually do this measurement. It's two completely different interactions that you as the classical system would have with that qubit. And so in one of those interactions, it doesn't introduce any uncertainty as to whether it was, in this case, plus or minus, because it's definitely minus. And so the interaction that I use to measure that allows that to fully come through, right? But in the other case, let me go back again, just so that we can visually compare both. So I didn't have this set up in sort of the most elegant way to just quickly change. What I would really want to do here is, in fact, let me just show how one would do this, right? So let's say I want to write a viz function real quick, and the variable I want to have is the measurement that's going to be called m, right? And so right here, we're going to make the measurement m. So now here I have a visualization function that's going to make these. And so let me now call my viz function just to make sure that that works. And the poly x operator, which is that plus minus question, is going to be the measurement that we do. So if I run the visualization function this way, I get this. Now, let's say that I wasn't measuring the plus minus question, but I was measuring the 0 or 1 question. We go back to our initial setup, right? Where here now I start out, if I ask a question where the interaction doesn't introduce any uncertainty along this axis, then sure enough, yep, it was definitely that state. But if let me actually just, so you see a difference in notation here because of the name that we've used. That's probably the more common notation that you're used to, 0 or 1. So this was just a sort of a live sneak peek into, okay, so we actually don't want to just be copy pasting all this code everywhere. So we've, through interacting with our students, we've discovered, oh, wait, there's an interesting question that we can explore here, but I don't want to just sort of rewrite or awkwardly copy paste code. So we can have one function that's now defined, right? And it makes this nice visualization, but it takes an argument of, well, what am I actually measuring that's going to show up here? And then everything else is handled by the computer behind the scenes, right? So now my visualization function creates this, which was the original picture that we had, compared to now if I want to do this measurement instead. So, and now we could even say, well, what happens if we've gone through X and Z, but what happens if I go along this other axis? Where now I'm measuring along this axis now, sorry, the left-right axis now. So here at all points going through this exercise, notice that the state, after having these operations applied to it, it's never along this left-right axis. It's always either along the 0, 1 or the plus-minus axis, no matter which of these particular operations we've applied. And so if I measure the left-right question, which again is just a different basis, so you can think of it as east or west versus north-south. If I ask a different question about this quantum state in my measurement interaction, then I'm always just going to get 50-50 in this particular case, because with this example circuit, at any rate, I've never put the state anywhere on this axis. It's always been either 0, 1, plus or minus. It's never been left or right. And so if I interact in a way that forces it to say, am I left or right, then I'll just get 50-50 in each of these cases. So yeah, I think hopefully that shows sort of the nice part about having, and especially if it's your first time going through and figuring out what all these options are doing, so it looks sort of as pretty as you'd like it to, that can take a little bit of time. There's lots of resources in terms of documentation, also in terms of we have let me not turn them on now, but so there's natural language input, where I could ask about the Planck constant just in natural language and get a Wolfram alpha result, for example. We could ask a language model like the thing behind ChatGPT, help me write some code. And so that can be helpful for, getting you to the point where you're comfortable, taking something like this and tweaking it on your own. But the other nice thing is that if something works and you see what the output is, you can always just sort of drag and drop it into whatever lesson you're wanting to do, right? And so we have some places where we encourage people to share when they've created stuff like this. It sounds like there's another question.
No, it looks very good, and I just want to say that first of all, the currency thing that I mentioned, I guess kind of forced analogy. It's much better to think in terms of north, south, and east and west. But then these three bases, then you have to give up on those two, and you end up basically on a sphere: up, down, left, right, forward, backwards, and that's really it. Yeah, because I don't have, I mean, I have northeast, southwest on a plane, but then I don't know what to do with the third one. So, but if you then think in terms of spheres, you're done. That's perfect. Thank you. Yeah. Excellent.
Yeah. So okay, so we can visualize some interesting things about some of these example circuits and trying to explore, well, so again, if we're just applying the quantum operators to the qubit, we started with a well-defined quantum state, and on the left, at every point along the way, we still have a well-defined quantum state. It's only when we take that qubit and we couple it to another system, in this case, us trying to do a measurement, that we might introduce some randomness into what result we're going to get when we take something that is definitely 0, and I say, all right, well, is it going to be plus or minus? And then, okay, well, it wasn't plus or minus, it was 0. So now we have some measurement uncertainty that comes not from a badness in our measurement device, but it comes from the quantum state. Before we measured it, it just wasn't in plus or minus, it was in some other state. So I think sometimes at least for me, when I was learning physics, a picture is worth 1,000 words. And so being able to have these sort of diagrams was something that I always try to do in my mind when looking at textbooks, but now with computers, we can do a lot to help our students, I think. So there's some more circuit examples, but I want to also get into another game I like that sort of gets into this idea of quantum advantage and why that's relevant. So there's this famous game called the CHSH game, and I think you all will be looking at the GHZ game during this course as well. So I'll stick with the CHSH, named after these folks for starters. But basically, the point of this game is that the referee is going to send 2 of these plus states, and so you just saw these plus states. They're not a 0 or a 1, right? So if I take something that started out as a plus state, so this is the minus, but it's the same principle. If I take something which is definitely along this axis, but then Alice and Bob are only measuring along the 0, 1 axis, they're not measuring along this plus minus. So these pluses, when I measure them, for sure, are they a 0 or a 1? That's a 50-50 shot of going either way, right? And so you can think of this as also flipping two coins, right? So one player flips two coins, hands one to Bob so that Bob can only interact with one coin, and one to Alice so that Alice can only interact with one coin. And then Alice and Bob aren't allowed to directly talk to each other. However, the question is, can they coordinate in such a way so that they can predict, and there's some specific what's called a Boolean function that, don't worry about the details. Basically, it's just answering a question about the coin flip results. Can Alice and Bob coordinate in such a way so that they can predict the results of this experiment well, right? That's the purpose of the game, and I won't get into why this Boolean function or anything like that. But that's kind of the big picture, is that Alice and Bob are trying to gain information about what happens here without actually talking to each other directly. And so, if you, again, this is that same principle that we were looking at before, but this can be as simple as visualizing the result without having to go through that fancy visualization. If you just measure this plus state, you get a measurement outcome. And even though you definitely started in the plus state, if I plot the probability, I'm going to get 50-50, 0 or 1. And I can simulate a bunch of measurements as to what that might look like, right? Because even though the probability distribution is exactly 50-50, as you know, if you actually flip coins, you're not guaranteed to get half heads and half tails, only if you do a lot of them, right? So we can simulate outcomes. So one strategy that Alice and Bob could use to try to make predictions about what they're getting in terms of these plus or minus states that they're getting, and then they're wanting to, again, they want to come up with some particular logical combination of yes/no questions related to these states they're getting.
They say you don't want to go into the Boolean logic, but I mean, there is Alice or Bob
XOR
is X and Y, right? So
yes.
Why you don't want to go into the Boolean? Why?
Just go into the Boolean.
Sure. Okay. Sure. So the particular Boolean function that they're trying to satisfy, right, is so when everyone measures things, so can Alice and Bob arrange it so that their bits, so Alice only has control over A, Bob only has control over B. Alice can interact with X, but not Y. Bob can interact with Y, but not X. So can it be arranged so that the logical combination of X and Y, so for example, if I get 1 and 1 when I ask this measurement question, then I get true over here. Can we arrange it so that this exclusive OR, where Alice and Bob are getting either 0s or 1s for their bits, gives the same result? So Alice's bit exclusive OR with Bob's bit, can that be the same as this bit and this bit, right?
Yes.
So
then they set up a strategy without communicating with each other to win this game.
Right. Yeah, that's the key, is they're not allowed to, because if they're allowed to like interact and then talk to each other, it's trivial, right? But the whole point of the game is that once they get their hands on this X and Y bit, they're no longer allowed to communicate directly with each other. So if you're not allowed to communicate after they actually can look at these random bits that they're getting, then one classical strategy is beforehand they could just say, okay, well, no matter what we get, we're just going to both say 0, no matter what Charlie sends us. So that could be a strategy that they arrange ahead of time. And so we can simulate this result where we get some X's and some Y's, some A's and some B's. And then we can make a little table that shows, okay, so did this satisfy the Boolean function or not, right? So if this is what I get for X, Y, and B, did Alice and Bob win the game? And so if you take a look at how well this strategy does, it tops off around 75% that Alice and Bob can win the game according to that strategy. But there's an interesting quantum strategy that you can do. So what you can do is, if you start where you've actually entangled the bits that Alice and Bob get. So in other words, Alice and Bob, this is still not violate, so in other words, Alice and Bob can communicate before the game starts, so to speak, right? That's just like what they would do with the classical strategy, where they say, okay, we're both just gonna, no matter what happens, we've coordinated, we're just gonna say 0 all the time. Instead of doing that, if you take two bits which are entangled with one another, so that this is what's called a Bell state. In other words, Alice and Bob don't know for sure whether their bits are both up or both down, but they know that they're not going to have opposite answers to what they get on their bit. So before the game starts, they entangle their bits. And now once they're entangled, they no longer allowed to directly communicate. But just because the bits started off entangled, now it turns out that if we compute, okay, well, what's the distribution that we get if Bob follows this sequence of operations and Alice follows this sequence of operations, right? So again, Alice is taking a look at this bit and interacting with her bit only based off of what this bit does. Bob is taking a look at this bit and only interacting based off of what that bit does. Through this particular quantum circuit, you can get a probability for satisfying, again, this is that Boolean function, right? So bit and same as bit or with the x's and y's, a's and b's. And you get a probability which can be computed exactly and turns out to be around 85%, which is better than what that classical strategy was. And so this is often used as a teaching game. It's actually not my favorite. So I'll be excited to see what you all think of the GHZ game, because I think getting into the details of these Boolean functions sort of distracts from the point of the quantum advantage. But it is a classic, so I wanted to include it. But at any rate, if you follow a classical strategy where Alice and Bob are both just, making their bit 0, no matter what they're getting from Charlie, then, that's doing pretty well, but it still tops off at a probability lower than what you can do if they start out with entangled bits. And so you can then also explore this and say, okay, well, in real quantum systems, there's going to be errors because they have experimental apparatuses and things like this, right? So we can even do a variation on this where we could say, okay, instead of having just this idealized setup where we are allowed to measure immediately, let's say that Alice and Bob both have some chance that their noisy equipment flips this bit and they don't have any control over that, right? So with probability PA, Alice's bit gets flipped before it has a chance to be measured. And with probability PB, Bob's bit gets flipped before he has a chance to measure it. So, we can deal not just with the idealized cases, but we can say, how does this affect our analysis? And so again, you can compute the same sort of distribution. You can simplify the result. In this case, it's a bit more complicated than the previous one. But once you simplify everything, so notice I'm using some functions to take what was a little bit more of a complicated initial result and clean it up a bit. But this is the idealized case where Alice and Bob didn't have any noise. But if you introduce noise, you can actually get a formula out that shows you how well this strategy of these operations will do if there's some chance that the actual experimental hardware has some noise in it. And so, we can see that if there's no noise, and then we might visualize this function once we've obtained it. If there's no noise in either Alice's or Bob's hardware, then that strategy gets that 85% win rate. If Bob has, let's say, perfect hardware, but Alice's hardware, flips the bit with some probability, then the strategy starts not being as good. And interestingly, there's a symmetry in the problem where, excuse me, where if this bit flip is sure to happen, so in other words, the probability that our apparatus did the opposite of what we thought is 100%, then it turns out that same strategy is equally as effective. In other words, it didn't so much matter, and that's again due to the specific Boolean function that we're looking at, right? So if both Alice's and Bob's bits flip because we're looking at this exclusive OR, right? If both of them are flipped, then there's a symmetry there, so it didn't actually matter, right? So again, this is one of the reasons why I love looking at quantum and physics problems, is that it brings in this concept of symmetry and geometry, and you can plot things and see in space visual representations of the effect of having noise in hardware, in this case, for example. Then, so I had, again, filing this idea of doing computational experiments, right? So then I had this question. I had never, looked at this question before the first time I did this little demo. So should Bob's strategy depend on the amount of noise in Alice's wire? So let's make, another circuit. So here we have this same idea. So this is that CHSH circuit where now, you'll notice if you compare to the previous one, let me bring down the idealized case just so we can see that. And again, this is one of the things I like about working in notebooks, is that if there's something that you want to move around so that people can see it better, you can just do that in real time pretty easily. So notice that other than my visual formatting of the measurements being laid out like this rather than all in a line, so here, instead of Bob doing a particular operation, Bob now has a choice of angle that he wants to supply as a parameter to his experimental equipment, right? The rest is the same. And Alice has some noise in the hardware, and we don't know what that is, so we're leaving that as a parameter too. Okay, so now this is like a noisy setup where we can say, all right, is there some optimal choice of what this parameter should be, given that we don't quite know what the noisy hardware is going to be? And I had thought that, yeah, maybe it should matter. But what we can do is we can proceed as before, where we run the circuit to get measurements. We apply some constraints that the probability of noise is going to be between 0 and 1. The angle is going to be between 0 and 2 pi. And then we simplify these somewhat complicated results. And then, again, this is just more simplification. We wind up getting a function that shows us how well the strategy should do given certain results. So here, if we see over in this corner right here, this was the original case where Alice had no noise and Bob had set this angle to pi over 4, as you can see in the original circuit. And so that was a good strategy. If Bob chooses different angles or Alice has noise, we see that it becomes a less good strategy, but still pretty good up to a point. However, there is also a point. So in other words, if you cross either of these lines, then Bob has a different optimal choice of what angle should be chosen, right? So if we cross either of these lines, rather than staying down here in this blue shaded area, Bob should switch choices and go up here in this region. So I had no idea that that was true until running the computational experiment, right? And so then we can simplify further. We can say, all right, so I see what this landscape looks like, but can I maximize this function according to these constraints? And it turns out that yes, you can. So there's a maximum here. We can do a little bit more work, which again, depending on the learning goals for your students and what part in their math sequence there are, you may or may not want to get into this example. But if you're used to the idea of computing a derivative in order to find minima and maxima, then that's something that they might well be familiar with. And so we can then solve, okay, where was the derivative equal to 0? And we see that this optimal wind chance, apparently, this pi over 4, which you can see a bit from the contour lines here. So this pi over 4 choice of angle, that's still the best choice of angle, no matter what the amount of noise is, until we cross that line. And then you want to swap over here, and then the optimal choice of angle is going to be this one, right? So in other words, even if there's some noise, I don't necessarily want to immediately change my angle. And so that's really interesting to me. I had no idea that would be true. I would have expected that Bob could maybe try to, based off of beliefs about how much noise is in Alice's machine, adjust this angle according to some complicated formula. But it turns out after you do all the calculations, not true. Turns out that when you flip this, when you pass this line as to how much noise there is, you should adjust your strategy. But other than that, just staying on this line and then on this line is going to be the best that Bob can do, no matter how much noise is in Alice's machine. So again, that's some of the code that goes into this is maybe a little bit more than what you want to first start into, right? But I think it's a really interesting example that once you're familiar working with some of these tools, there's all sorts of interesting questions that students might spontaneously come up with, right? So, we've talked about this idealized case, and this is a common complaint that we get in physics courses all the time, is, okay, well, sure, that's the idealized case, no friction, no air resistance. What really happens, right? And so we can actually start to model that by thinking, okay, well, how do we take our idealized circuit and start to extend our model to try to understand these questions better. So let me pause there just to make sure that we have plenty of opportunity to ask questions and go into detail about topics that others are interested in. I can show a little bit more about the quantum framework or about mathematics in general, both in terms of teaching calculus and all sorts of other things. But let me make sure that we have plenty of time for questions and anything like that.
Right, so if there are any questions, go ahead and write them in the chat or just speak up and ask the question, please. Any questions, any kind of questions? I'm not sure exactly how wide the use of Mathematica in high schools is or the middle schools. As far as IU is concerned, I guess we have a site license. And then having some affiliation or association with IU, I guess gives you access to that. How much of this, John, can we use directly in Wolfram Alpha or?
Yeah, so real quick, as I'm answering that question, let me show you something that is a Mathematica specific feature. So the negative answer to that question, and then the rest, what can be used. So what I'm about to do is say, what does this code do? And this is one of the new features that we have. What I've done is I've turned on the chat features here so that we can ask a language model to help us out writing some code here. So it's taking a minute because my internet is slow today. And so here the large language model says, oh yes, this code is building a quantum circuit operator. Here's what it's doing. It's explaining that this particular part here, which is exactly right, is representing entanglement between the bits that Alice and Bob has. Then it's recognizing that, yes, these are Hadamard gates and controlled Hadamard gates specifically. Okay, so again, I've not let it see the entire notebook. I've only let it see up to here. But so again, if you have some working code and students or instructors or anyone are wanting to see, okay, what is this doing? How do I unpack this code here because I'm new to it? So this is a either Wolfram Cloud or Mathematica specific thing to be able to ask a large language model, which is a nice feature. And the way that I did that is I enabled the chat features. Now, in terms of things that you can do in Wolfram Alpha. So Wolfram Alpha has a lot of functionality for being able to do all these simplifications and for working with the equations. And so those I would do in Wolfram Alpha. The block plots and some of these quantum circuit specific things. So that is something that requires this quantum framework in order to be able to create this block plot so easily, right? Now, if you look at the code, I think I have the GitHub link too. Yeah, I do. So all the code for how the quantum framework works is right here on GitHub. So if you are really curious, you can look into and see, okay, so what Mathematica code was it that allows one to just say, give me a block plot, and then we get a block plot. So what we call low-level operations, having to roll your sleeves up and write a whole bunch of code, that is there. You can access that through Wolfram Alpha. You can write that in Mathematica without using this particular framework. However, this particular framework has made a lot of that more convenient than having to create this 3D visualization with something more complicated than just asking for a block plot, right? You would have to use functions like graphics 3D, and this is a arrow, and you would have to know how to annotate things. And it's not so bad actually once you get to learning it. But if you're brand new, I would recommend starting with something like this. And the way that you do that, so this framework is completely once you're in your environment, that could be the free version of Cloud, it could be the downloaded desktop version. Once you're in your environment, you can just run this once to install it, and then after you've installed it, you never need to install it again unless you want to get like an update, let's say the latest version or something. You just run one line of code that is that I need the quantum framework for being able to do what comes next. Let me actually show you what happens if we haven't done that. So what I'm going to do, I'm going to pretend like I'm having a fresh start here. So let me quit that. Yep. And then let me say 2 + 2 just to restart everything. and everything's starting back up. And now that we've got a result, you see that after you've got everything initially started up, of course, 2 + 2 is calculated very quickly, but that first one was just restarting everything from scratch. So you see that with things restarted from scratch, these blue displayed things, these are not defined in my current session of this notebook I have open, right? So if I run that now, nothing happens because it's not defined. So once I've got my framework installed, I run this once, and now, oh, yeah, okay, so that happened because I didn't actually exit out of everything before starting this. But at any rate, once we have that loaded in, then I got my error because I actually hadn't completely quit out of everything. So it's saying it's double loaded and it's unhappy about that. But if you start fresh and load it in, those would be those black symbols. And let me actually quickly save as 2, and then stop that share real quick. And then I'll go back to the fresh one just so I can show you what I was showing you a second ago. So I'll stop sharing, turn that off, and then show you what loading that up fresh looks like from a genuinely fresh start rather than forgetting to exit out of something else. While I'm doing that, any other questions that we have?
I guess not.
Okay, so all right, so here's a genuinely fresh start. So here's that blue symbol that wasn't defined. So now if I load this in, it isn't double loaded on accident like I had before. And you see that now this is a symbol which is black instead of blue. And if I evaluate it, we do get a state, right? So again, the takeaway here is that much of this functionality exists in Wolfram Alpha. However, the quantum specific, being able to quickly ask for some of these things, to do that, you're going to want to use this packlet. And the way that you access that packlet is it's installed once, and then anytime that you want to start a new session, you just remember needs Wolfram Quantum Framework, and then all of these convenience functions will be defined so that you can quickly do these things without having to worry about coding them up yourself.
Excellent.
Thank you.
Thank you. Okay, so now we got to 10 o'clock, which is when we have to stop. I want to thank John for this excellent lecture. We recorded it. So we're going to post it. Once I get the confirmation, I'm going to put it in YouTube. Then I'm going to send you a link in case you want to use it at all or refer to it. But it should be posted by 2 p.m. today. Thank you once again. This was so good. We do GAZ, and the CHSH game is in the book, in the Terry Rudolph book. And then I keep avoiding it on account that it requires, if you do things by hand, you have to do it and get a percentage. And so it looks like overwhelming. Whereas with the GAZ, you always win. And I guess I have a simpler way of actually doing that. So thank you so much for doing the CHSH game for us. We'll refer to this video again when we study that part in the book.
Sure. I mean, I agree. I think I would only do the CHSH game if you're working with a computer. If you're wanting to have it be clean, I totally agree. I think that GHC is the way to go. Which is interesting that CHSH started out well before we had tools like this as one that people would make students do by hand. It's important to keep in mind. I think that's a reason why many students might not come away with as fond a feeling for quantum physics as, let's say, that I did, because I really liked doing that kind of stuff. But it can be very tedious, right? So if you're, if you have a tool that you can present the game, set up the game, compute the probabilities, show the probabilities, do all those sorts of things without having to go through the tedious by hand calculations, I think that's a different story.
It's like you do the experiment.
Yeah.
Just do the experiment and you say, wow, amazing. I believe it. That's all. Yeah, well, thank you once again. This was just outstanding. Thank you so much.
Thanks. Yeah, and again, there's practice homework problems I saw for this week. I always like to give my students basically a head start on those homework understanding questions. So definitely, if any of that code that's in that notebook helps anyone, feel free to take a look, check your work.
Thank you once again.
Thank you.
Thank you. Yeah, we'll see you. Bye-bye. So I'm going to go to stop recording, and then I'm going to discontinue, and we'll see everybody on Friday, tomorrow.
Yes.
Bye-bye, John.